Breckenstein over here. You guys are crazy madman, I'll tell you. Okay, so just let me get this over here a little bit more. Whoa. Alright, so we just finished up. I just finished up, well, me and the team, we collaborated. As far as this math tomb that this is becoming. Yeah. Put you down inside of here. So we got the Hadron Collider going. We're working with some black holes, some apples, some physics problems, some quantum physics problems, and astrology and physics, which we'll be getting into some later. Also, I want to do some stuff with some code I found on here. I want to make sure I integrate that into here next. But this was my big black body radiation and Bernoulli's into the history of the universe with cosmic radiation background, right? You know, I want to be able to slide those through the wormholes on the bottom for the black hole, infinite past, infinite future, infinite past, today's future. It's not as pretty as that other one, but the conceptual models, as we're turning that axis and actually looking at it and trying to describe some Hawking radiation here, some heat off of these equations, we want to generate an axis that changes it in a field where nothing acts on. So as soon as it does that, it's going to make some shift, some gravitational stuff. It's going to make it all the pixies mad, or all the EM waves and everything like that, just to be furious at you. And again, that's from taking it, the black body problem, to the observation of kind of what a black hole is. The Breckenstein bound is about the conservation of information. The limit this piece of paper is going to be able to have to describe what a black hole is, but hopefully it gives you that satisfied, feels like I'm looking at a black hole kind of a thing. Because you look at this thing, come on, you tell me. You tell me you ain't just staring at the center of a black hole looking at this thing. And that's kind of the general thing, because this actually gets some pretty heavy topics. You know, this is some real math, and these are really good math equations to help you practically try to learn this material. What's going on here with the spin direction on all these things and certain types of interactions traveling around the pipe, losing it, changing drag, getting past a part with power and intensity of wave function. That's going to aspect a lot of things like Bernoulli's just standard aspect. Pipe to a pipe. If A1 and V1 and P1 all are congruent, are constant, then it shares AV constant. A1 V1 equals A2 V2. And that's to say these conceptual model black hole, energy, gravity, singularities across the board, as long as they're congruent and the flow mechanics is flowing through it, it's basically acting like a black hole. Now, we're not actually harnessing a black hole, but we're taking some of these math principles and we're integrating them. We're saying connecting these features, it changes a mass, it changes the system, kind of like a temperature or an index of distances change how things work, and much more practical on your feet version of what it does, but it still allows for this quantum function to hopefully work at the macro and micro level, and again allow some kind of teaching aid to it. Now again, I'm up for some debate, but they're already in bricks, right? Easy enough to change around, easy enough to move, try different positions and do things with, especially in while we're getting into some of this, before we get into full-scale topological models in breaking down equations like these. These are pretty good fundamentals. Breaking down even more so as we get into completing the square, or how those types of mathematics work to indicate the law of conservation of information, or the limits that a black hole is going to teach you. It's not going to be able to give you photons and everything. It's going to give you a heat emissions. Now, what it ate is a intensity level of what those things do. So when you get into space-time and stuff like that, these topological types of universal lensing, gravity, density, time dilating systems kind of give you multiple wave functions when I'm looking at somebody. Usually you get that conversation when you're talking about this mathematic. Are they red shifted with a large wave function, or are they blue shifting to this with a real fast tight line? Like, I get that. I'm not really seeing any kind of dark matter or dark energy. I'm really getting a lot of the baryonic harmonics. That's what I'd look to. Or I'd look about to change it because of that spectrum, right? Because I see you kind of gauging in and out a little bit from the student's perspective or the teacher. Hey, fucking pay attention. Got time, energy to efficiently train you engineering inside here. Make sure you're catching it, because that is as simple as what it is. A, pay attention. IH, rational, heat, light, sound, values of putting that through the pipe and making sure it doesn't rupture that valve in Bernoulli's to figure out the pressure and make it rise 100 meters off the ground from the pipe, or the pipe's diameters down, up, big or little to big diameter. Gravity's going to help that flow. Medium to little should balance out if I'm pushing for gravity because of the pressure rating inside of there. I'm not going to have to worry about putting too much up on that. It should 1-to-1 ratio if the mechanics are right. And then you get to actually Bernoulli's an even tube, but without the gravity, any kind of differential of that when we're dealing with the approximation of the air pressure outside for inside. Lots of entropy outside. Inside that house, zero movement, zero system. So as soon as a 100-mile-an-hour wind starts coming over your house, it's a lot of pressure on the inside of the house. And using that house, in this case for Bernoulli's, in particle science and quantum physics, or any types of math or fields that might be going in there, becomes this wind shear under that fact. There's a lot of stuff traveling down the pipes coming down at you, you know what I mean? And it's got a lot of up and down and bottoms up. So key color spectrums are not coming in here. Key bases are based in prime and cicada levels. So it's not really colorful, but this really isn't supposed to be either. Remember, all this later on still gets condensed into whatever math book with better examples, training aid systems, and syllabuses to those ideas, because you want them in that form. Equally, like, it in itself is a test. It's got those uncertainty principles to it. It's got that Dirac's equation base to it. It's got extra spectrums of energy, antiphoton, Z-boson, heat and light for Z-boson and Higgs. But then a color of light, iron, in the spectrum of the noise that the color of that sun makes, so those are the types of things that help you determine the mass of the black hole, the spin of the black hole, how long it will live in dimensional axis or dimensional analysis of ranging the parts, but to fundamental levels under those ideas, so they become more appropriate when you hear something like how many fish there are. I'm sure it's pretty comprehensive to general relativity and things like that, but there's still, even at the margins of approximations, Torino talks about energy, but there's a whole bunch of heat, light, and sound quantified now. Each individual broken down by their spectrum is not what you get when you hear Hiroshima or Tickling the Tail of the Dragon for 15 megatons when you're expecting 5 or 6 megatons. The approximations there are a little different to, again, that dimensional analysis to fundamental levels or functional models of in-stone mill MOSs and other variables on that. So catch you on the next one.